All right. Welcome everybody back to class. Now this week in class we covered bearings. Wow, it has been a long week. The reason why I know that is because next week we're covering gears, and I haven't talked about that yet. Just to recap that lecture, find out what load you need on your bearings, and then find a bearing that can handle it. And that's about it. What you're going to see for a lot of machine design pieces is that it really just comes down to understanding what you need it to do and then finding the mechanism that does that. That's it. Machine design does have a lot of design principles associated with it, of course, but it is a lot of component selection. And understanding the math behind how to figure out how to pick stuff is valid and it is necessary. Your homeworks for the next few weeks, I'm going to shut this door. Your homework for basically the rest of the semester, your homework assignments are going to be design problems. You probably have seen the shaft design problem that I posted that's due tonight. Casey figured out the secret to how to solve that, so if you really want a hint on how to solve that problem, he's the guy. But it's something where I want you to engage more in design settings. Now, I'm not giving you a design problem for bearings because it's really not that hard. Bearing design is, yes, okay, if you want to get into thrust loads on bearings, it starts getting complicated. But oftentimes manufacturers will even state maximum thrust capabilities, that kind of thing, on bearings, which is useful. Understanding the difference between journal bearings and ball bearings or roller bearings is also important, but I covered that in lecture. You guys are doing a reading assignment, and I mean, I can give you a quiz, but it'd just be what's the difference between them, and just be regurgitating exactly what I told you. So I told you at the beginning of the semester that I was going to give you a spring break. Usually what I do in my classes is I don't assign homework over spring break because I am a firm proponent in the idea that every once in a while you need to live and stop breathing academia. You have a lot of homework due today. But I am going to give you a reading assignment over gears and pinions, and it will be due in 2 weeks. Now that means in 2 weeks you have 2 reading assignments due, but you will not have any assignments due next week, aside from your project 1, and that's just because I moved project 1 back. Okay? So this is your fall break. I called it spring break. It's spring break where there's no spring. Okay? So that's usually what I try to do, and even though we're doing an accelerated schedule, I need to honor the fact that at this point in the semester, everyone's dead and we're all just walking around like we're trying to remember where we're at. This class has been difficult, as promised. I'd feel bad about that, but you all came in here and I told you it was going to be hard. Be sure to spend some time this weekend on your project. It'll be due next Friday for you guys. It'll be due on Wednesday. What you're going to be handing in for your project is you're going to show me your computer and show me a model that works. If you don't have a computer, and neither you nor your partner has a computer, then we'll have to figure something out from there. But I do need to see your SolidWorks model, okay? And I need to see how it works. So the purpose of what we're going to talk about in lecture today, I was hoping to check all of your models today, but as I said, I pushed everything back a week because I really was not impressed with the quality of designs that I showed. And some of that comes back on me because when I talked about mechanisms and the design of mechanisms, I didn't really do a very good job of doing that. So I want to go back and try to cover some of the material I should have covered when I introduced that to you. And hopefully this will give you a better indication of what you would expect to see in this type of a setting. Okay, so let me see if I show up. When it comes to mechanism design, you're really looking at power transfer. So power transfer for a lot of mechanisms is very simple, okay? How does power come in? How does power come out? Now, linkages is the idea that you can have power transfer occur in many different ways, okay? The purpose of a linkage is to convert your power from one modality to another. And that's really what this comes down to. How do you convert power? Now, for your mechanism, you're bringing in, for your input, a rotational power output, power input, where you have both a torque and an angular speed. Torque times angular speed is your power. That's how you calculate power. So knowing what your torque and your rotational speed is, that's how you figure out your power. Now, as a clarification on this, you have a full rotation where theta is equal to 360 degrees. Theta is the change in, well, delta theta, I should say. Okay, you have a full revolution of your axle. Okay, so as you're looking through your power transfer, you are looking for a mechanism that inputs rotation 360 degrees. Okay, this goes into your linkage, or your set of linkages, or your multiple sets of connections of linkages. And the output from this is going to be some kind of linear motion. And it doesn't necessarily have to be precisely linear. It can be a number of things. It can be an actual angular movement. Here, every time I lift my leg, this is two distinctly different rotational movements, okay? But I could do this and just lift one leg, and it does move upward 7 inches. But we'll talk a little bit about this. Okay, so the purpose of your linkage is how do you take a rotational input and have a displacement-based output? The mechanisms that we've talked about in this class so far have been cams. Cams for the input, you have 360-degree rotation. And for the output, you have a linear displacement. Well, that sounds perfect. That's what we want, right? Do not give me a cam. Why? Because of this. Most cams have 1/4 of an inch to a 1/2 inch displacement. Why? Because it takes a lot of accelerations in a cam. Having a 7-inch displacement for a cam is ridiculous. Now you're talking to an engineer right now, well, you're listening to an engineer, I should say, who spent his PhD dissertation trying to design a 9-inch cam. Ultimately failed, ended up coming up with something that had a 4-inch lift, and finding out that you can get a 4-inch lift if you make your cam about this big. If you make your cam about this big, your cam weighs about 150 pounds. That's a little unnecessarily big, if you ask me. Just a little, yeah, just a little. So, yes, cams are great for taking a full rotational input and producing linear output. Do not do that in this project, okay? This project, you will intrigue me as I then turn around and chastise you. But I mean, there's fun in that, so we'll make it fun. We also talked about 4-bar linkages, okay? And there are different kinds of 4-bar linkages. You all did the readings. One of the kinds of 4-bar linkages is a crank rocker mechanism. And for a crank rocker, you input 360-degree rotation, and you output a rotation about an axis point that is a fixed angle. Okay, hence rocker. Okay, it rocks back and forth. So this by itself is not sufficient to solve this problem. Now, one of the mechanisms we didn't talk about in class was this one, which is a crank slider. And it's not like the kind of slider you get down at White Castle, you know. Look, it's a crank. Here, your input is 360-degree rotations. Again, that's your crank piece. Here, your output is a linear displacement. So let me sit down and design for you the simplest solution to this problem, because this does everything you want it to do. And if I tell you this solution, and you do this solution, you will satisfy the requirements of the project. However, it will not be the best design. And we'll talk about that too. So for a crank slider mechanism, I hate this projector so much. It's exactly the content you guys show up to Machine Design to watch. Your professors struggle with machines. Yeah. Huh?
Try turning it off.
Have you tried unplugging it? You guys are terrible. So a crank slider mechanism, I'm going to go ahead and show you a very basic crank slider mechanism. Okay, here is crank. Here's your coupler. And I'm going to put a block on this. And I'm going to put this block between two walls that are rigid and cannot move. For the purposes of your design, this would be like having it be in a slot where this is rigidly connected to ground. And this also is rigidly connected to ground, okay? Now, as this crank rotates upward and downward, the coupler acts as a liaison between the crank and this slider mechanism, okay? This is your link number 1, this is your link number 2, this slider is your link number 3, and the ground is your link number 4, okay? As a representative, if you wanted to have an actual mechanism, you could have something where your ground linkage looks like this, has a slot in it, has a spot where the crank comes out, has a coupler, that goes into maybe a round slider, a wheel or something, and that goes inside of your slot. And then as this crank travels around 360 degrees, it just slides inside of that. And then this component here would be fixed to ground, okay? You then take this slider, or this bolt here in the slider, and you extrude it out, connect it to the rest of your leg, and it moves up and down like that. Fun times. Okay, simple solution. To get 7 inches of lift, all you have to do is make sure your crank is 3.5 inches between this point and this point. That's it. I've just solved your entire problem. Now, I did say that this is not the best solution. Okay, so looking at this in the sideways configuration, let's say here's the rest of my leg. It is mounted directly to my sliders so that it can't rotate. What happens in this configuration when I apply a force to the bottom of this object? It's going to create a really large torque around this crank mechanism. Okay? In fact, that's the maximum torque that you can create, is when the crank is up and perpendicular to that coupler mechanism. Okay? You have your maximum transmission backward, so any resistance on this side, it's going to be really difficult for this mechanism to overcome that. Hopefully you don't burn out your motor. You'd have to get a really powerful motor that can produce the torque capable of generating a force in this mechanism, so inputting torque, outputting force, linear displacement, that is capable of continuing to move even if your object hits something right there, like if it's climbing a stair or something. Okay? It's all about power transmission. So I recommended to you that you use a 4-bar linkage. Again, you can use this. You can use a variation of this. That's fine. You have a rotational input. You have a linear displacement output. That's fine. But what I would also suggest looking at is a crank rocker mechanism. Now, a crank rocker mechanism in itself does not solve this problem, as I said. Because the issue with a crank rocker mechanism is you're outputting an angle, an angular displacement. So if I draw a crank slider mechanism, got my coupler, got my rocker, got some kind of a ground linkage, fixed body. Maybe this is the body of a robot, maybe this is a table, maybe this is a wall. This is something that does not move, okay? If I have this mechanism right here, and I fully rotate this crank around 360 degrees, this object here will pivot about this point like so. A power transmission comes as a torque about this point. However, at every point, this power transmission, if we look at a single position, represents a physical, small, circular displacement and a force associated with that. The relationship between rotation and translation is simply that r theta is equal to x, and T over R is equal to force. Those are your relationships. So the farther away from your axis you get, the larger the displacement you get. The closer to the axis you get, the larger the force. This is true for all mechanisms. And this is one of the fundamental concepts of linkages. When we bring in a torque and an angular displacement here, we have the ability to directly affect how the force and displacement comes out of this. I had a question in the last lecture about, what kind of motor would you want to put on this? At the end of the day, it doesn't matter the kind of motor you put on this, because the relationships that you're deriving are how it transfers from 360-degree motion to your F and your X, or your F and your V, because these multiplied by each other equals power. These multiplied by each other equals power. The time varying displacement, that's your velocity. These multiplied by each other equal energy. So, looking at this mechanism here, okay, or looking at another mechanism that we're going to be discussing next week. Let's say I have two gears like this, intermeshed, interlinked, hooked together. If I make one rotation of this smaller gear, will this larger gear experience one full rotation? Does anybody think yes? I am seeing a whole lot of everybody saying no. Why? Anybody know? Huh?
Smaller.
It's smaller, and the idea is the circumference of the first circle is equal to pi times the diameter of your first circle. The circumference of your second circle is equal to pi times the diameter of your second circle. These 2 points at this location experience the same displacement. When your car tire is driving on the road, your car tire is moving at the same speed as the road at this location, which happens to be 0 miles an hour at the road. They have to travel at the same speed, or else they spin relative to each other. Gears are designed so that they don't spin relative to each other. Okay, and every time you peel out, your tire connection to the ground is actually traveling faster than the ground itself. But unless your tire is squealing on the ground or spinning on the ground, it is traveling at the same speed as the ground. That is your boundary condition. They have the same velocity. These points right here have to have the same velocity or they slip relative to each other. The velocity of this point is r times omega. r1 times omega 1. The velocity of this point is r2 times omega 2. And both of these have to equal each other. r1 omega 1 equals r2 omega 2. We're going to get into this next week, and I wasn't expecting to get this far. But the idea is, if you rotate this one full rotation, this circumference, because diameter 1 is smaller, is less than this circumference. You're not going to have a full rotation of a larger circle because this distance right here doesn't travel as far. Similarly, if you were to spin the larger circle once, it would actually cause this smaller circle to spin multiple times. More than one full rotation. Okay, so comparing the speeds, the angular speeds here, the connection between them changes. So the simple thing is, if you want something to go faster, you just gear it up. Or gear it down, sorry. Where you start at a larger gear, you go to a smaller gear. And then maybe, you'll have a gear shaft that comes out like this, and then you go to another larger gear, and then that meshes with a smaller gear. And then that one has a shaft that comes out that goes to a larger gear, goes to a smaller gear, and you keep doing that. And you gear it down. That's a transmission. That's what a transmission does. Okay? It's a very simple process where you can take your angular speed and greatly increase it. Drake told me yesterday in 350 that there was a guy who took Lego Mindstorm pieces. You were there, weren't you? Yeah. You were there. You were in that conversation. And he took it and he created a Google gear ratio, which is a little excessive, but that's all it is. You just continue to do this over and over again. Okay, so a Google gear ratio here means you have a gear spin 10 to the 100th times, and the one on the very end spins 1 time. That's what it means. Okay? Why don't we just do that in reverse? Where we have 1 rotation, and then over here it produces 10 to the 100th rotations. Why don't we do that?
You're inputting too much power to just 1 rotation.
You're right. Because the idea is it's all about power transfer. Okay? These two multiplied by each other equals power. You have to put in the same amount of power to that gear system no matter what. Right? So if you rotate it once and you're putting in, maybe 3,000 pound-inches of torque, that's the power that goes through your system. Your power in your system does not increase suddenly. You don't just have a place where it jumps. And here's my power generating mechanism. It's a gear. Look at it, it's pretty. You don't have that. What you do have is a constant amount of power being transmitted through your system. Some of that power is going to be lost due to friction. So you can't help that. Some of that power is going to be lost due to vibrations and sound. Another sources of loss, it just happens. But if you assume no power loss, then you spin this once, and on the end of it, you get a Google rotations out of that. Then the amount of torque that you put in is going to equal the amount of torque that comes out divided by a Google. Power in equals power out. Your power in to this system is omega t. Your power out of this system, I'm going to just write P again, apparently. Apparently I got a P. Is omega t2. This has to stay true. Your angular speed multiplied by your torque has to be constant. In a 4-bar linkage, this is also true. Now, when I said that 4-bar linkages have unique timing attributes, this is true, but these change dramatically. At some point in your rocker mechanism, your omega equals 0. Because it stops, it reaches its maximum displacement. At that point, your t value is infinite. So, pretty cool feature there, having infinite force translation. A lot of mechanisms will use this as a lock. They'll actually use a rocker, crank rocker system as a lock. You rotate the crank to a certain location. You don't need your crank to go full 360 degrees, you just need it to lock. and it will use this infinite torque transmission at that position to lock. Because no matter how much force you put in, you cannot make it rotate back outward. Okay? So, with this concept, you get the same amount of power out as you put in. We now have this relationship. If we're doing a crank slider mechanism, we now have this relationship as well. Both of those are true. Force times velocity is your power output for a linear displacement system. Now, this, your force times your velocity, if you wanted a force to come out of this, let's say you have a pin, maybe you create a slot, and you have another mechanism in here that slides like this, such that it can't move up and down. Okay, and it's got a, 1 degree of freedom joint right there, where it can rotate relative to your rocker. A 2 degree of freedom joint, because it can also move up and down. But it's constrained from moving this way. You will get a linear displacement out of that. That's all it takes. You can take an angular mechanism and produce, you can take an angular rotation and produce a linear translation by attaching it to another mechanism. Your 4-bar linkage can be merely one mechanism inside of your overall linkage. And it should be. If you choose to use a crank rocker system, this should be only a part of what you do. You'll have to have something else that turns this into a linear output. Okay? Now, when I said this is better than a crank rocker system, applying a force here, let's say this was your leg mechanism. If you apply a force here, that force is carried in part by this pin. You do not have the perfect 1-to-1 ratio of force input goes straight into the crank. Okay? You do have some help in resisting movement in this direction. Now that said, if this thing gets hit here and it causes the rocker to rotate, well, that's your worst case scenario, because that's basically having a crank slider system where your force is pushing on your slider directly perpendicular. Okay? That is the worst case scenario. There's nothing you can do about that. But in this case, the force direction means that this can be carried by this rocker mechanism. In a crank slider, if I go again with a crank slider mechanism, okay, if we were to apply a force in this direction on the crank slider mechanism would be able to handle it perfectly. There would be no, you can push on this infinitely and you're only pushing on ground. That's it. So that's kind of the difference between these two types of systems is, yes, this is also a 4-bar linkage, and yes, this has great application. But if you want to prevent force transmission from being carried back directly to your motor, maximizing your power output, it's best to make it so that the direction of the force that's going to be applied, make it so that it doesn't go like this. Now you could connect a linkage to this, have it go over here, make it more complex such that as this rotates, it lifts something else up. You could try to do something like that. I don't know if that's really going to help you super duper much. It would, because it changes the force direction like that. But you still have the same power in, power out opportunities here. Okay, so I have exhausted most of my lecture points on this. Does the idea of what a linkage is supposed to do make sense? Most of you guys are in 350. It's all about input, controller, output. Our controller here is our linkages. That's what we're doing. We're using the linkages to take power, transform it into something, and output it as something different. Okay. Are there any questions on what I'm expecting for you for your project? Okay, if you want to show me your linkages, I will look at them. I will give you my opinion. Otherwise, the rest of these 10 minutes are for you. I'm going to shut off the live stream.